So this afternoon, my name is Prince Dai. I'm one of the organizers. So this afternoon, we're very happy to have Haim from Weizmann Institute to give a talk. Yeah, so
thank you. Thank you very much, Chairman, and I would like to thank also the organizers for putting together this very diverse and interesting workshop and inviting me to give this talk. And today I would like to add the kagome materials to the list of flat band materials and the interesting phenomena that are induced by them that were already discussed in this workshop. This is a very exciting collaboration between us, Scanning Tiny Microscopy Group, and the DFT group of Bingai, the group that really initiated the interest in this material that I'll discuss today, nickel-3 indium, is Joe Chekelski's group from MIT that grew the material and did the first characterization of potential strange metal behavior in a kagome system. And we had very interesting collaboration with the local group of Shimiao, with Monica and Fang, and others to really understand the origin, how a kagome flatband can give rise to strange metal behavior. So we've seen already actually today and yesterday several examples of flatbands which are commodity in high demand in condensed matter. And there are different ways to realize flatbands which are close to the Fermi level or act close enough to be active. One of them is heavy fermions, where we have field states, F electron states, which then interact with some metallic band, which crosses the Fermi energy. And through this interaction and hybridization, an emergent flat band forms at the Fermi level, hybridizes with a light band, and we get these composite light and heavy electrons that give rise to this characteristic. Sorry, I don't have a pointer. I'll try to use the mouse. That give rise to this characteristic Doniak-like phase diagram with a typical critical point. Yeah, okay, never mind. Typical critical point above which there are strong fluctuations that basically give rise to the collapse of the Fermi liquid theory. Quasi-particles are no longer good description for the electronic states because the interactions are too strong to define them. They're not stable enough. And out of these new metallic, strange metallic states, many interesting phenomena like high temperature superconductivity may emerge. So a field that has been studied for many years and still is. And here I'm showing you an example of ytterbium, rhodium, silicon, one of the canonical materials that give rise to this kind of phenomenology. And what is usually seen spectroscopically in scanning tunneling microscopy or planar junction spectroscopy is this kind of spectra, peak and a dip in the density of states or the tunneling density of states, where the peak is associated with the flat band and the dip is associated with the Kondo hybridization, the hybridization gap that forms in the material. So this is the standard spectrum that signifies these heavy fermion systems. And let me also show you a result on cerium cobalt indium 5 that was discussed yesterday by Laura, where again, you can see it's tilted sideways, but you see the peak dip structure around Fermi level, and also in the quasi-particle interference, which is STM's way to image dispersion. You see that there's a band that kind of flattens out towards Fermi, and this is the hybridized light band that hybridizes with the heavy band, forming the heavy fermion behavior in this material. Or that was the claim in this paper. And as we've heard just before from Matthew, we of course have other ways to induce flat bands, and one of them is twisting bilayers of graphene towards the magic angle, which forms these flat bands that still have dispersive parts around the gamma point. Of course, they give rise to very diverse correlated phase diagrams. And as Matthew noted, there's a lot of effort to try and understand or resolve the phenomenology or some of the phenomenology in magic angle twisted bilayer graphene as a heavy fermion system where the heavy bands are the flat band and the dispersive part around gamma plays the role of the light bands, and the hybridization between the two give rise to some of the phenomenology that is in an experiment. And basically what I would like to do today is try to contribute our share to adding the kagome flat bands into this growing family of flat band materials that maybe exhibit behavior which is similar to heavy fermion physics, although there are no F electrons in nickel-3 indium, but still similar behavior is observed. Because this is not a kagome workshop, let me give you a brief introduction to kagome band structure and the interesting features in it. And it's actually, I find it very instructive to construct the kagome band structure by adding atoms into the triangular unit cell one by one. So if we start with triangular lattice, this is the typical dispersion that you will find. And actually already there's an interesting feature of a saddle point at the endpoint in the triangular lattice band structure, which gives rise to a logarithmically diverging density of state. So potentially also a feature that could give rise to correlated physics. And already here, this saddle point is coming because of interference effects. Basically, if the electrons hop along the collinear bonds, they form a constructive interference, but then in the normal direction, this zigzag pattern gives rise to destructive interference, and therefore, if you go from M to K or to gamma, you get electron and hole-like dispersion, which is exactly what gives rise to the saddle point and to the logarithmic diverging density of states. Now let's add the second atom to the triangular unit cell, which of course gives rise to the well-studied graphene or hexagonal lattice. So now each atom brings another band to the band structure, and in graphene or hexagonal lattice, we now get another copy of the saddle point, and of course a symmetry-protected Dirac point between these two bands. There have been many efforts to dope graphene towards its saddle point, but it's just too far from the neutrality point, more than 1 eV away. So there has been some success, but it's very hard and non-trivial to examine the diverging density of states of graphene at its saddle points. Of course, graphene is also where topology started with the Kane-Millet model when you consider spin-orbit coupling. So also this kind of physics exists naturally in the triangular lattice family of structures. And now when we add the third atom to the unit cell, we get the kagome lattice. So we add the third band to this band structure, which is the flat band. And basically this third atom gives rise to the destructive interference when you hop around now the atoms on this kagome ordered or triangular sharing atoms, which localizes the electron within the Star of David structure, and the localized electrons basically correspond to the flat band. Now, nothing really protects the flatness of the flat band in kagome lattices. So it's really the challenge of the crystal grower or material scientists to find kagome materials in which the flat band is as unperturbed as possible, because what we want to have at the end is a high density of states. The more it disperses, the less peaked the density of state is. And of course, to find materials at which the chemical potential is at the vicinity of this flat band. So The kagome band structure gives us, and one of the reasons in my group, we like to study this family of materials so much is because it gives us several opportunities to look at Dirac physics, topology, and flat band physics, heavy fermions, both from the saddle points. The two saddle points, unlike in graphene, the two saddle points are not identical. In kagome, there is a pure type and a mixed type, which have slightly different phenomenology to them, and then the flat band, which will be the main focus of my talk today. So, kagome systems have been known to exhibit many instabilities. The most common instability explored is a charge density wave, potentially of exotic nature. Some of them are thought to be time reversal symmetry broken, chiral, still debated topic, but this mainly comes really from the saddle point physics. So at the energy of the saddle point, the Fermi surface is very simple. It's simply hexagonal, which gives rise to very strong nesting between the opposite edges, and this gives rise to the charge density waves. But we would like to talk today about the flat band physics, and there's one interesting work I would like to refer to from Bertolt Jack that grew thin films of cobalt tin, which is another kagome material, and gated them towards with doping, with doping of iron, doped them towards the Fermi level, towards the flat band, and at some doping, he sees a spectrum that seems that the one plotted in red, which starts to seem resemble a Mott insulator. So presumably the flat band, once is slightly doped, just splits into an upper and lower Hubbard bands, and this is how the interaction energy is lowered. What happens in the material that we studied would be different, and the main reason we think that the material that we studied, nickel-3 indium, avoids the fate of Mott insulator is actually because it has not only a flat band at Fermi, but also light bands. And cobaltine doesn't have these light bands, so its fate is a Mott insulator. And in our case, we believe we indeed form a strange metal. So let me now move on to talk about the material itself, nickel-3 indium. So it's a rather complicated, has a rather complicated kagome structure in the sense that it's not composed only of a single layer of kagome structure, but actually a bonded bilayer of kagome lattices formed by the nickel ions, which you see here in dark and light green. And one of the interesting aspects of it, if you calculate its band structure, you find indeed there's a flat band which at neutrality is located very close or at the Fermi level. And ARPES, the weight of it is about 90 MeV. You can identify other kagome-like features in the band structure, like the saddle points at the endpoint. And in ARPES, maybe the flat band was slightly apparent around the Fermi energy, but they could identify other bands in the band structure, and by fitting them to DFT, they could already see that there's a strong renormalization of the band structure, and the flat band width, which should have been around 90 MeV, turns out to be more on the order of 30 MeV. But by far the most interesting observation, at least to us in this material, was the transport or temperature-dependent transport, which, as you can see here, at low temperatures starts quadratic, but then deviates into something that looks more like a linear temperature dependence, which is deviating from the Fermi liquid paradigm. And if you now, or Czekelsky's group, map the power of the temperature dependence across the temperature magnetic field. Sorry, I don't know why the panel is stuck there at the bottom, but it's the magnetic field axis. You see that at low temperatures and high magnetic field, there's a Fermi liquid behavior, so the power is 2, but then across a crossover line, it crosses to a power which is not 2, which is something that contradicts the prediction of the Fermi liquid theory. And this is the main signature of the strange metallicity that forms in nickel-3 indium, presumably from the presence of a flat band, a kagome flat band at the Fermi level. So what we wanted to do, of course, we do scanning timing microscopy, is look for the spectroscopic origin of these strange metallic behavior and understand what are the moments in this kagome system. There are no F electronic states. And can we see the strange metal behavior in STM? Right. So this is a topographic image of one of the crystallites that we've measured. So this is a thin film of nickel-3 indium, which has amorphous nickel and indium, and among this amorphous structure, there are crystallites of crystalline nickel-3 indium. So we had to sputter, anneal them, and find those crystallite regions. But as you can see, we were successful in doing it, and we can indeed see the kagome surface of nickel-3 indium and take spectroscopic measurements of the surface. And what immediately became apparent is that everywhere we measure on the surface, when we look close to the Fermi energy, which in STM is zero bias, we see this peak deep structure, which exactly resembles the spectra seen on truly heavy fermion systems, like ytterbium, rhodium, silicon, cerium, cobalt, indium-5, and so on. So, of course, this material should have been a metal, and even though it should have been a metal, we see this peak deep structure that we wanted to characterize further. So one thing we could extract is the depth of this dip coming from some kind of condo interaction or hybridization, or this is at least the interpretation in the classical heavy fermion materials. So we measured the spectra at varying temperature. This is how it looks like at 4.2 Kelvin. And basically, we see non-monotonic behavior. It is maximal right at the crossover temperature between the Fermi liquid and the non-Fermi liquid behavior. And in the non-Fermi liquid part, it seems to be suppressed. But at least the main message from this to us was that this deep peak structure that we measure is sensitive, is aware to the crossover between the Fermi liquid and the non-Fermi liquid states in this material. Sorry?
Zero field.
Zero field. This is zero field. We have also field-dependent data, and it follows the phase diagram in the right way. I don't have this. This is all at zero field. Sorry, the axis is temperature.
So alpha there seems to go below 1 for temperatures above 5. Do you see that? Do you guys do transport too?
Let me try to get rid of this panel. What is this? No. Because all my labels. Okay, sorry. What was the question?
I was just asking, so if I look in the regime at zero field, what you're labeling NFL there as a function of temperature, right?
Right.
Seems to correspond actually to alpha less than 1. And I don't quite know how to read that color graph, but how small is alpha given?
So alpha, above this line, alpha is varying. It doesn't have a constant value.
Right.
It has a constant value within the Fermi liquid part of the phase diagram. And there is a strip at which, sorry, it ends up, here it's a round one. It ends up being below 1. It doesn't take a specific value.
Right, but does
in transport.
I mean, so it's starting to curve like this, right?
Right.
Okay. I'm just asking because, okay, so that whole upper region from like 5 and higher, that would all be in this alpha less than 1 region.
Right. This would be the NFL, the non-Fermi liquid part of the phase diagram.
Peak dip out to? Like, what's the highest temperature at which you see?
So we could follow it up to 10 Kelvin
It's still there.
without the tip changing and us reliably following the, yes, it's still there. Sorry, note that the axis here doesn't go to 0. It started at 2. So there's still a finite healthy dip that we can quantify there. Yes. The next thing that we wanted to understand is really what are the moments in this kagome, who plays the role of these the F electrons in a proper heavy fermion system. And for this, we use this first this analysis where basically we take use of the huge redundancy that we have in every time we take a spectroscopic map. So what you see on the top left part is that the IDV map taken over a surface of, actually this is a different kagome material just for the sake of demonstration that we've measured. Basically what we do in STM is then measure pixel by pixel over the surface, but our grid is never commensurate with the crystal structure, not in its size and not in its symmetries. We use usually just a cubic grid, and here it's a kagome lattice, which means that at every point we're probing presumably the same unit cell at slightly different point. And we do it time and again. So as long as we are able to put, to define the lattice over this grid, we can collect these different points that we probe the unit cell within a super resolved single unit cell. So instead of having very lousy resolution per unit cell, we end up with a single unit cell that now has thousands of pixels collected from throughout the field of view. And now we can resolve very carefully the distribution of the wave function within a single unit cell. As long as, you know, all the unit cells were identical, so we need to find regions with sufficiently low disorder when everything is uniform enough for this analysis. Drift should be minimal for this analysis to work. So now I just copy this single super resolved unit cell 6 more times, and we can see the periodicity of the wave function across the lattice. So we apply this method to nickel-3 indium. First of all, the DFT calculation predicts that the wave function, which is mainly contributed by DXZ orbitals. However, as you can see, the DXZ orbitals don't capture only the flat band, they also contribute to the light bands, Dirac-like bands that disperse around the flat band. So this is not really the local moment that produces the flat band, but the flat band is mainly constructed by these DXZ orbitals, and they are localized within these triangles, corner triangles of the kagome crystal. So this is where DFT predicts that the flat band should be localized. But now we can examine where indeed it is localized. So this is super resolved density of states, taken at different energies of this lattice. And what you see is that far away from the Fermi energy, below and above the Fermi energy, the wave function localizes on or off the triangular corner triangles of the kagome lattice. So all these distributions respect the underlying symmetry of the kagome lattice. But then when we image the wave function at the peak, where we believe the peak is related to the flat band, to the kagome flat band, we find a distribution that does not agree with the prediction of the DFT. Basically, the wave function localizes on a nickel ion, which is not where it should be, according to a single particle calculation. And we can also now, after we have this high resolution of every pixel within this unit cell, we can go to specific points within this super resolved unit cell and plot the full spectrum within this exact point. And this is what I show on the bottom right. So on the nickel sides, the orange curve, we see very clearly the peak, the flat band localized. And on the 5 minutes? Ah. Oh, wow. So should be done now. Okay. And off the nickel sites, we don't see any reminiscent of the flat band. The peak goes away, but the dip is distributed all across the surface. So this is where we started the discussion with Shimiao's group. And basically, they developed the concept of compact molecular orbitals that really try to address what are the structures, for example, in kagome materials that play the role of moments, and they can take the 60 plus orbital DFT calculation, turn it into a tight binding, and from it distill the superposition that exactly captures the flat band energy. And if you're interested, you can go to Monica's poster. She can tell you a lot more about it. And as you can see, it is indeed a superposition, in this case, of atoms from the two kagome layers. So dark and light green are localized on the two kagome layers. And this particular superposition, what it produces what you see in the magenta line. So this is exactly the degree of freedom that produces the flat band. And as they calculated, I'll go quickly, it is localized exactly on the nickel atoms, as we see in calculation. And when they calculate the tunneling spectra on the nickel side and off the nickel side, they see exactly the dip and funnel-like line shape that we, peak dip structure that we see in experiment. So this agrees very nicely and allows us to identify really this destructively interfering path of the electrons over the kagome lattice as the moments that play the role of localized electrons in this kagome system. And finally, what about the strange metal, the collapse of the quasi-particles? So again, we have this method of quasi-particle interference that allows us to image the band structure of the material. So this is a QPI pattern at 3 different energies. And this is how they disperse in a cuts along gamma M and gamma K. And what we immediately observed is that right at the energy of the flat band, this peak at minus 15 millielectron volt, we see a suppression in the intensity of the quasi-particle interference that has no reason to occur in the single particle band structure. Moreover, this data was taken at 4 Kelvin within the non-Fermi liquid phase. When we now cool the system and repeat the measurement at base temperature within the Fermi liquid phase, we see that this dip completely goes away, which is, of course, against any thermal broadening scenario that should result in the opposite. The more we warm the system, the more features wash out. Here we start with a well-defined dip at high temperature that disappears when we cool the system. So the system really seems to lose its coherence when we go to 4 Kelvin within that energy of the flat band. And maybe just a final comment. So here we are imaging not the flat band. With QPI, we're imaging the light bands, those Dirac bands. And for a long time, we thought they are just spectators or nuisance in this experiment. But actually now what we understand is that their interactions with the flat band is basically what gives rise to the strange metal. If you wouldn't have the light bands, because many of the material searches search for flat band materials, kagome metals that have flat bands at the Fermi level, it is important to remember that if you want to see strange metal-like behavior, you must have also a metal in your system. So there should be some sort of light bands that would interact with the flat band and give rise, presumably, to the strange metal behavior, which is carried by the suppression of the quasi-particle weight. So I'll leave the summary on because I'm out of time. But yeah, we believe kagome materials are really a diverse platform for studying this kind of flat band behavior. Thank you.
Any questions? He used up all his time, but anyhow, yeah. Yeah. No.
How does this those and those are give a lot of surface material.
So this is a zoomed in topography. All the point spectra and the folding of the wave function were taken at regions which are free from impurities. And the quasi-particle interference data was taken in regions that have impurities to scatter the electrons. I don't think we looked carefully on the spectrum right at the impurities, but they are interacting with the electrons because we could clearly see the QPI ripples around them. So, yeah, not sure.
Okay, yeah.
Actually, related question, what happens if you try to do QPI on a large scale map? Is it still good or does it, so in other words, how much disorder do you have if I just look at the local denser states distributions?
Well, you know, always there's a sweet spot of how much you must have some disorder to get QPI, but then it gives you some structure factor that starts to wash out the data. I don't know if this is something I didn't try to think if there's specific limitations to this material being a strange metal.
I just ask because there's some of us severe microcognitive worked on disorder roles and strange nodes.
I see.
Sort of. So I'm just curious, if I look at large scales, if we look at the local nodes of states, does it look, pretty clean? Like, or do you see what looks like sort of multi-fractal?
So as much as the peak dips structure represent the strange metal, it does not necessitate disorder on the scale of 100 nanometers, which is like the clean spots that we could get. This is super robust. Suppression of the QPI, we can only measure in the presence of disorder. I don't know how much it changes with the density of impurities. We didn't do these kind of statistics. But I'd be happy to learn what is the prediction for the dependence of this state on disorder.
That's fine. Yeah.
Thank you very much.